I was saying like we'll spend like around 40 to 45 minutes on coding problem, and I'll keep last 10-15 minutes for feedback.
Okay, sounds good.
Cool. So this is the problem. Like you have an zero index integers array of
Mm-hmm.
length n, and so basically every number you are at first position, like zeroth index, and
Mm-hmm.
every value represent like how many jumps you can take from any particular index forward. So basically, you can go to let's say for example, your current index is I and your value is x. You can go to I plus 1, I plus 2, up to I plus x.
I see.
So you have to reach to the last index n minus like last index which is n minus 1, and you have to return minimum number of jumps required.
Okay. So, okay. Each element nums I represents maximum length of forward jump. If you are at nums I, you can jump to any I plus j. Okay. And then j is between 0 and nums I. Right. Okay. And I plus j is less than n. Turn the minimum number of jumps to reach nums of n minus 1. So return the minimum number of jumps to reach the last element of the array.
Correct.
Okay, cool. And all right. So let me just restate the problem real quick. So you have an input array, and the input array
Mm-hmm.
contains a bunch of numbers, and each number represents the amount of indices you can jump from that index, and you want to start from the 0th index and end up to the last index in the minimum number of jumps.
Mm-hmm.
Does that sound correct?
Yes.
Okay, cool. And then let's see. So I'm going to look at the example. So 2, 3, 1, 1, 4. The output is 2 because it takes 2 jumps. From the 0th index, you jump 1 step, and then you jump 3 steps. 1, 2, 3. That makes sense. Is there always going to be one solution?
There could be multiple solution, and you can
Mm-hmm.
like multiple ways of reaching in that many steps, right? So basically, let's say for example, it could also be possible that you had two here. One way was like to
Mm-hmm.
go to three and then to four. Otherwise, you could can go to two and then to four. But in
Okay.
both case, jumps are two. So you are just concerned about the number of jumps. So in terms of
Okay.
output, there is going to be always one possible output. Yeah, but there is a possibility that you cannot reach to the last index. In that case, you can return
Mm-hmm.
-1.
Return -1 if there is
Yeah.
no solution. Okay. Perfect. And okay. I think that covers everything. Okay. Cool. I'll just go into approach. I'm gonna think about it for a little bit. I guess starting from the 0th index, you're always going to start at the 0th index. So then you're only considering the. Oh, could I use the whiteboard?
Sure.
So you're only considering the indices you could reach from the 0th index initially.
Mm-hmm.
And then interesting. Let's see. I think this sounds like a dynamic programming problem.
Mm-hmm.
Possibly. Where I guess we'd be keeping track of the number of jumps to the end, and then updating that as we go. Sorry, I'm writing on my notepad. So if we have that example, 2, 3, 1, 1, 4. So we look at all places reachable from 2, and that's index 1, and that's index 2. And then and then we can consider each one. So if you go to index 1, then you could definitely go to the end. And that's because the value at index 1 is greater than or equal to the length of I guess, yeah, the end minus the index value at the index. Okay, so that's probably important. And then we could look at the next one and see that 1 is not greater than or equal to, what is this, 0, 1, 2, 3, 4. So 4 minus 2. Let me just write out these examples real quick. So the value at 1 is greater than or equal to n minus 1, which is 0, 1, 2, 3, 4, minus 1 is 3 is equal to 3, and then index 2 that's greater than or equal to 4 minus 2, and we see that 1 is not greater than or equal to 0, so that fails. Okay, so it seems that this is our condition. But let's see. That's only the condition to reach the end. And that doesn't consider any intermediary steps. So, this is a really hard problem. Let's see. I feel like this is a dynamic programming problem. I haven't really worked on dynamic programming questions.
Okay.
Could I have like a little hint about how that would work?
I think yeah, so I think you are right that this could be solved with dynamic programming problem, but there is other way to solve it
Uh-huh.
using graph also.
There are other ways using,
Uh,
sorry,
yeah, you can solve it, consider it as a graph problem also.
as a graph problem. Okay, that's good to know. Oh, this one's pretty difficult. Okay, so we have a node. Um, so like 0. Um, how do you represent this graph? So if we have nodes at every index, 0, 1, 2, 3, 4, and
Mm-hmm.
then I guess the values would represent edges connecting from wherever you could reach,
Mm-hmm.
something like that.
Mm-hmm.
And so 3 means there'd be edges like that.
Mm-hmm. Yes.
And 1 is just like one connecting edge. Okay.
Mm-hmm.
And so if this was a graph problem, what would be the problem? You'd want to get to from point A to B the minimum number of steps. So that's the minimum number of nodes visited. Um, good. Sorry, just thinking about it. Um,
Okay. What are you thinking now?
I'm just
I think
thinking.
you correctly modeled it as a graph problem, right? But
Hmm.
and those edges would be directional. Like you can go from 0 to 1 or 0 to 2, but not a
Hmm.
vice versa. You cannot come from 1 to 0 or 2 to 1. You can always go forward, right? Okay.
Could only go forward. Yeah.
Mm-hmm.
Um,
Uh,
I guess with that information, then you can kind of make a sub problem. So like once you traverse
are
to a
you
node,
okay? Are you aware about graph algorithms?
um, I like, yeah, but I don't think I could implement them like A star
Okay.
and like, yeah.
Are you aware about traversal graph traversals?
I'm aware of tree traversals, like
Okay.
DFS, BFS,
Yeah. So I
um,
think BF what
contextual
do you
trees.
think? Can one of them solve this?
Um,
This is a tree,
I
right?
guess.
Because there is no cycle and it's always going forward.
Oh, you're right. That's very true. I believe depth first search then, because you're trying to go to the end.
Okay.
Yeah. So, that's so true. Okay. So maybe if I represent this as well, there are cycles, right?
Yeah, but they are not directly
What?
cycles, right? You cannot start from
The
node and come back to that node.
True, yeah. Okay.
So do
Yeah,
you think you would be able to implement BFS, breadth first search, or we should move to some different question?
so yeah, maybe a different question, I think.
Okay.
I'm not sure.
Sure.
Well,
Mm-hmm.
you said depth first search, right?
Breadth first search.
Breadth first search.
Yeah. Why do you think like because you want the smallest path, right? So
Mm-hmm.
breadth first search will give you smallest path. That
Oh, okay.
wouldn't, right? You go level by level
Yeah.
and you want like to reach as early as possible. With this, your
So,
index zero would be your source, and you will stop your the breadth
mm,
first search when you reach to the last index.
so breadth first search would be better because you hit the end of when you hit the
So
end,
first time, yeah, you know that
you
this
could
is the,
terminate.
yeah, you can terminate. In that first search, you don't know, right, whether you have reached through shortest path or non-shortest path.
Right. Okay. I think I could give it a shot then.
So,
PFS. Okay, so the algorithm is from the source. You would okay. You would use BFS, and then once you hit the end node, once that's reached, then you terminate. Okay. So BFS. Okay. Uh, 1, 3, 4. I guess. How much time do we have left?
we have around 20 minutes.
30 minutes. Okay. 0, 1, 2, 3, 4. So then this would be the 3, 3 to 4, and there's also 1 to 4 as well. So it'd be like this, and then the BFS would travel there, then it
Mm-hmm.
would travel there, and then it would terminate. And so in the implementation, I guess the first step would be to represent as a graph. Represent as graph. I just use this. And then as graph. And then run BFS. Given the graph representation, we can run BFS by, I believe it would be a queue, right? So we would have some queue. So if I was doing, I'll just create a queue. And then like this one. Okay, so you would add the roots. And then while there's elements in the queue, you would I believe pop and then add the children. So then at 0, you would pop 0, add the children 1 and 2, and then you go back, pop 1, add the child 4, and then pop 2, add the child 3, and then I guess while the queue, and then we check the win condition if the value. Okay, so how are we representing these actually? So if the index, the values of each node only represent edges, and so that will be handled in our graph representation. What we care about is the index, which we could store as the value of the node. So if the node is equal to n-1, then we have reached the end, and we need so we need something to keep track of the distance, right? So for every path we take, it's going to be a new thing we'd want to keep track of, and it's not necessarily like a binary tree. Obviously, it could be a bunch of different paths. So what would be a good data structure to keep track of paths? We can so every time we pop from the queue, we get hold on, sorry. Okay, so we're at 0, all queue, then queue.pop, 0 comes out, add 1 and 2. Every child you add is a different path. I think that is always true. So we could do like, when we're adding the children, that would be for child in children. We would oh wait, we don't necessarily have to keep track of all of the paths because we just need the minimum path. So I guess once you hit the end, oh, okay, yeah. So at every iteration, we could just have, okay, min distance is equal to 0, and then every iteration we just increment, because you're going by depth, you're going by levels. And so you would just increment this, and then by the time you hit the end, it's going to be the minimum distance. So we would want to just return the min distance there. So yeah, you don't have to keep track of paths or anything. That was kind of a detour. So I think that's good for running BFS as far as representing the graph. Given an array, 2, 3, 1, 4, 1, 4. I guess you would construct a node. I'm not sure what's the best way to represent it, a graph here in the code.
I think like you always don't need to represent a graph, right? So you can go through this what you write a code, right? You just need to think about how would you identify all the children.
Okay. Yeah.
You don't need to build a graph, right? So yeah, this looks good.
Right.
Maybe we can go back to text and write a code.
Okay. Sounds good. It's my first time using this interface. Do I just write it here or?
Yeah.
Okay. Okay, so it doesn't necessarily have to be like something executable.
Yes, that's okay.
I see. Okay. Well, it says we're given an array of integers. Can we just assume that we converted that into something that we could run this algorithm on? Or do we have to implement that as well?
You have to assume it's as an input to be available as an integer array and another integer, like, yeah.
Okay, so it has to work with an array of integers. That's okay.
Yes.
Okay. Well, in that case, so I do need to somehow represent. Okay, add children. Okay. I'm gonna do it in Python. I don't know if there's like text highlighting. Is that?
Sure. Yeah, you can write in Python.
Oh, cool. Oh, what? Cool. While so from collections imports deck, then you want a function. What should we call it? Zero index array numbers. Minimum path that takes in an array of or we call it jumps, a jumps array, and that's it. And then we want to so Q is equal to Q We'd want to add something here first, but I believe it's possible actually. And then I'm just not sure right now how exactly to represent it to add into the queue, but let's see. Okay, so if you're at the first index, let's say 2, that means there's an edge from 0 to 1 and 0 to 2. Meaning the children from that node are indices 1 and indices 2. So when you when you add something to the queue, I think for now, maybe, I'm not 100% sure, I'm thinking we add like the index. So let's just add like 0, the first index.
So you need that.
Then,
Okay. You add an index, that makes sense. Yeah, you add an index, that makes sense.
Okay, cool. And then when you pop it, that's going to be the current, and then you look at all the possible places you could reach from that index. So that's going to be all the children. So, and then you want to add those to the queue. So how would we do that programmatically? We have cur, the value of cur is going to be jumps of cur, and then using that value, that's all the children. So for I in the range value, you're going to add right, because if it's 2, then you have 2 edges. If it's 3, you have 3 edges. And then you're going to be adding indices incrementally from there. So you do q dot append I. I'm not sure if these brackets are necessary.
Not I, right? It would be like current plus I plus 1, right? I will range from 0 to L.
You're right. Current plus, so from 0, and then I is from 0 to val. So yeah, it would be current plus I plus 1. Perfect. Okay, so you add those to the queue, and then we're going to keep track of min distance here. And then if
your min distance should be level, right? You should not count the number of nodes. I don't think like you will be incrementing the min distance every time you reach any node, you pop any node from the queue, which won't give you a min distance. It will end up calculating number of nodes. Right?
Yeah.
Maybe you can add min distance as a tuple in a queue. So you can add like 0, 0, that to reach 0 you need 0 distance, and then use that to add the next one.
I see. So
and here like your queue will also give 2 things, current and disk, right? You will have like disk plus 1.
Disk plus 1, perfect. Yeah. Perfect. And then we have our win condition if cur I guess we could put this up here. So
Perfect.
if cur dot cur is the index. If cur is equal to length of jumps minus 1, then we've hit the end, and then we would want to return distance there. And then there's no way that distance wouldn't be the minimum distance because we're just building up. And so once you hit the end, it's going to be the minimum. If there's no solution, that won't be hit. And so we could return -1 here. And I don't know if this while would just go on forever. I think it wouldn't, because if you add elements to the queue, you would just pop so you hit the end and there's no cycles, because the children that you add are always going to be greater than you're not going to backtrack. And so there shouldn't be any problem with this running forever. So yeah, you just return -1 here. Cool. I think let's run that with the example and see what happens. 2, 3, 1, 1, 4. So is there a way I could do whiteboard and the coding environment? Is that possible?
No.
Probably.
At least not
Okay.
on this part.
Okay, that's fine. So here we have our queue. We instantiate with a tuple with the 0th index and the 0 distance, and then we pop, and then we see that the current is, so length of jumps minus 1 is going to be 4 here. Current is 0, and so we go on to here. The val is jumps of, so this array is jumps. Jumps of 0 is 2, so it's going to be 2 here. And then we increment through from range like 0 and 1, and then append cur, which is 0, plus phi, which is 0, plus 1. So the first tuple is 1, and the distance is going to be incremented. The second tuple is going to be cur plus 1 plus 1, which is 2, 1. So now if we have our queue, currently we have 1, 1 in there, and then we have 2, 1. So those are going to be in the queue. And then now we pop the next one. And so we could get rid of all of this. And let's see. So the next one's going to be 1, 1. We pop that. So we're working with 1, 1. Now cur is not equal, this could say, it's not equal to 4. This cur is 1, so we move on to here. Val is jumps of cur. Jumps of 1 is 3. So we have 3 for val. And then we append 3 different tuples, which are going to be, so cur is currently 1. And so we'd have 1 plus 0 plus 1, which is 2, and then distance is currently 1, so it would be 2. That's the next tuple. The next tuple after that is going to be 3, 2, and then 4, queue. So yeah, we
Right.
see we hit
We,
our
yeah, you
solution
will
here.
hit once you will pop it out. Yeah, you will hit it once you pop it out. What is the complexity of your solution?
Time complexity is, let's see, you're going through, so in a graph representation, go back to the whiteboard. Okay. BFS, I believe, is B plus E, number of vertices plus number of edges.
Okay, but here that would be the case when you visit every node once, right? But here you are not maintaining any visible visited thing, data structure for representing like which nodes are already visited and skipping them.
Okay, so it would be faster because we're not keeping track.
Yeah, so maybe can you consider adding that? And what would be the right data structure to maintain that?
Sorry, could you repeat that? Sorry.
So can you somehow maintain the list of nodes or the array indexes which you have already visited?
Maintain a list of nodes that I've already visited, yes. We can have a, what's it called? We could have a dictionary, and then if we visit a node, which we could do after we pop, if it exists, then we could just set something, and then sorry, what was the point of the visited tracker?
So you should not end up visiting some nodes multiple times, right? So for example, let's say this is a bigger array, right? Let's say this is kind of a bigger array. What will happen is you will reach this node 4 from 3 jumps from here, from 3, and 1 jumps from 1 also, right? So you might end up recalculating everything again.
Oh, I see. For computing. So by maintaining a visited, we could store the shortest path to that.
No, you don't even need to store the shortest path, right? You just need to ignore it. You don't need to add it back into the queue, right? If something has already been added into queue, you don't need to re-add it. That's it.
Right. Okay, yeah, that makes sense. So then you could look into our queue, and then if so then we'll calculate our next index. It's going to be curve plus I plus 1. If next index is not in visited, and we add and we append it to the queue. Yeah. And then I guess we don't even need to, we just need to make it a set. Not really sure how. think you add, yeah, you add to a set. Or no, it's fine. It could be a dictionary. I'm not sure how to set.
Cool. I think like we almost finished over 45 minutes. So let's pause
Okay.
for a feedback.
Yeah.
I think yeah, I think like you went through problem statement, you shared your understanding about the problem, and so that to make sure that you understand it properly, you clarified
Mhm.
few things like which were important, like will there will always be one solution, and we
Mhm.
discussed like there could be multiple optimal ways to reach the last
Right.
index, but we just need to return the length and not the actual path. And we also discussed the possibility that it is possible not to reach to the end of the end of a array.
Mhm.
And you were right that you mentioned that it looks like a dynamic programming problem,
Mhm.
and you were upfront about like why it could not be solved with dynamic programming. Okay. But
Mhm.
the one thing which you could have done is at least you could have shared dynamic programming is nothing but a optimization of on a recursion, right?
Mm.
So at least you could have shared a recursive approach, and then you could have said that, okay, uh, this is a recursion, and I know this could be optimized with dynamic programming, but I don't know about dynamic programming much. That could have been a better way.
Right.
Yeah, so that would be something which you can consider.
Okay.
Then we discussed that it could be modeled as graph problem, and you were good at modeling it as a graph problem, considering every index as a node, and each being there from that node, that index to every index in the array to which you can reach. Um,
Mhm.
yeah, I think like you can reach, and then you needed some help that to understand that this is very close to uh, trees. So what these graph is called as like directed or cyclic graph. So there are no directed cycles in the graph. And you
Mm.
were able to, you needed some help to understand like why BFS is a better choice than DFS, but at least yeah, you were listening it properly and implementing it. Again, like you
Mhm.
implemented a good code for taking care of basic DFS, and but yeah, your initial implementation wasn't calculating the distance properly. It was calculating the number of nodes. So
Right.
we
Right.
modified it, and you understood it. And then I think like you again needed some help to understand why visited needs to be there. And
Mhm.
yeah, I think like uh, I think like you did show that you can learn the problem, but at least like basic understanding about graph is something like what is normally expected. Maybe I will recommend you that practice some more graph problems.
Okay.
Um, cool. I think yeah, that is the feedback from my side. Do you have any question for me?
Um. Yeah.
Mhm.
So overall, just better fundamental understanding. Do you think like I don't know? I think I was a little concerned about the amount of time I was taking just to like think. I don't know. It just seemed pretty quiet. Do you think that would be a problem? Um,
I didn't understand the question.
just like the amount of time that I was taking just thinking about the problem. I
No, I
know.
think that was okay. I think like that was
Okay.
okay. Just about like the gaps in the like understanding about the basic algorithms. Then that would be
Okay.
the only improvable area.
That would be the only one. Okay. So communication was good.
Yeah, communication
Uh,
was superb.
okay.
Even yeah, even the problem solving was superb because like once I give you some hint, you were able to
Mhm.
use that hint and modify your solution. So there is no issue in that. Implementation wise, also it was clean. But
Mhm.
yeah, so but if you had understanding about like how that algorithm works, you could have implemented it without need of any hint or something.
Okay. Cool. And I guess just curious, like if you were in charge of hiring, that would be
Leaning no higher.
what?
Leaning no higher.
Medium, no hire.
Leaning. So I would say that soft no higher. So looks
Okay.
like so basically it reflects as like candidate has potential, but based
Mhm.
on this interview, he did not perform well. Um,
Okay.
the either way of handling those things is if you have a good hiring, like you have showed a good in problem solving algorithm in some other round, then you
Mhm.
should be hired, or you can also be considered for some follow up interview.
Okay. Cool. Thank you for the candid feedback. Really appreciate you taking the time for this. But,
No
yeah.
problem.
Thank
All
you.
the best for your practice. Yeah.
Yeah. Thank you so much.